Hello friends, welcome to my channel. Let's have a look at problem 543, diameter of a binary tree. Actually, this is a follow-up video for today's daily challenge problem. So in this video, we're going to explain a solution based on recursive depth-first search. So first, I'll read through the problem statement to digest the requirement, and then we do the analysis, and finally we share several formats of code from more redundancy to more clean codes. So first I'll read through the problem statement. So given the root of a binary tree, return the length of the diameter of the tree. So the second paragraph defines what's the diameter of a binary tree. So it's the length of the longest path between any two nodes in the tree. This path may or may not pass through the root. So this is actually one important assumption or a remark. So the length of a path between two nodes is represented by the number of edges between them. So in other words, that is all the nodes minus 1, right? So this is the main statement. So here is several examples. So in example 1, so the output is 3. So actually we can look at this path, for example, the path between 4 and 3, right? So we have 4, 2, 1, 3. So there are 4 nodes. In other words, the length is 3. So similarly, we can look at 5, the path between 5 and 3. That is 5, 2, 1, 3. So the number of nodes in the path is also 4, so the length is 3. So in this problem, this is also the maximal possible length. So in the second example, so there is one root, then there's a left subtree, so that is 2. So the number of node in this path is 2, so the length is 1. So this is also the output. So the constraints or additional assumptions for this problem are the following. First, the number of nodes in the tree is in the range given by the closed interval 1 and 10 to the power 4. So 1 tells us that the tree as a whole is not a null tree, and the latter 10 to the power 4 gives us the upper bound about the number of nodes, which also defines the problem size. So the node values are bounded in between a negative 100 and a positive 100. In particular, it can be 0, it can be negative. So with that said, we are ready to do the analysis. So as we have mentioned several times, so for the binary tree or tree in general, so this is can be regarded as a recursive abstract data structure. Therefore, when we meet problems related to such data structures, we can first think of recursions and to see if we can write recursive format of solutions. So here in this video, we're going to give a treatment using recursion. So we're going to do traversal using depth-first search. So this video or this solving of this problem is a revisit of problem 543 here. So after we solving problem 2246, so the longest path with different adjacent characters. So the idea and the solution format here is very similar. So to that of 2246 for sure. So there are actually a number of problems in Leetcode which has such a flavor, right? So we involves diameters and paths which are not necessarily passing through the root. So the idea is actually very simple. So for each node V, we want to find 2 pieces of information. So we write like this: the function f of V. So it returns 2 pieces of information, L and R. So here L is the length of the longest path starting from V and the next moving towards the left. So similarly, you can define or interpret R. So if we use this information, then the longest path, downward passing, right, passing through V is nothing but the length or the number of nodes I would say. So the number of nodes, this is more precise. The longest path here is L plus R minus 1. So minus 1 means that we adjust the double counting for the nodes V itself. So here I would say this L plus R minus 1 is the number of nodes in the longest downwards. This is not downwards. This is the longest path passing through V. So here V being the smallest level index, right? As say 4, 2, 1, 3. So the smallest index in 0, right? Downwards, right? So we have from 1 we have downwards 1, 2, 4, and we have 1, 3. So the length will be 3 plus 2 minus 1. That is 3 plus 2 minus 1. That is 4. So this 4 is actually we interpret as the number of nodes. So in this problem, we need to return the number of edges. That's minus 1 again, right? So in the recursion process, we could update the maximum number of nodes running from all possible longest paths. So for this update, we could use an attribute, or we can use a non-local variable. So this is the very standard or routine. So before we do the code, let me first emphasize one point. So here, first we are going to regard the length as the number of nodes in the path, and then when we do the return, we just need to minus 1 to accommodate to the current problem assumption. So with that said, let's first do the coding and then make some comments. First, I'm going to use an attribute for update, right? So here I'm going to use self d or diameter. So let's say this is 0. So here I'm going to store the maximal number of nodes, right, in the path, or in the longest path, in the longest path. So in the process of doing a recursion, we're going to continuously update this attribute. So this is the step 1. Step 2, so we're going to write dfs helper function. So this function, so let me write like this, dfs. So we're going to accept a node. So let's use root to represent the node. And then what we are going to do here, so we're going to return the length of a or the, let's see, longest downward path starting from root in the person. So we're going to return 2. So the length is the left winding or right winding, right? So in the process, we also update the d attribute. So this is our overall thought in the first version of the code. So first, let me write a stop condition or base case. So if not root, so we're going to return 0, 0, right? So this is actually very routine. So now, so let me write L equals 1 and 1. And then, so this 1 and 1 will count the root itself, right? So this is one node. And then let's do the traversal for the left. So for the left subtree, we have a left and R again. So let's see dfs root left. So similarly, we have R, the right subtree, we have L and R again. So dfs root right. So with this piece of information, we can get L, right? L increment by the max of LL and LR. So this will be the longest path, or the number of nodes in that path, starting from root and winding towards the left. So similarly, we can do R. So this is R, L, R, R. So now, once we do this, so let's update this D. Then with this L and R status, so we know that the longest path passing through the root and with the root at the smallest level indexing will be L plus R. then -1. So -1 means that we want to cancel the double counting for the node root itself, right? So then what we're going to return is L and R for this process. So this is the hyperfunction. So next we are going to write the problem logic and return, right? So for this we just need to call this DFS function. So here it returns something. One way we do this is like this. So right, so we have DFS, the root will be 0, right? So or we can write so let's see what we do. This is root, just the root. So we're going to write root. So or we just regard DFS as a worker, and then we do the job, and then we are going to return. So we're going to return self D. So notice that D here I'm storing the number of nodes in the longest possible path. So in order to compute the length in the problem, in the sense of the current problem, we need to return self D -1, right? So with that said, I guess that's about it for this solution format. So here, let me first do a check. So it passes the one example. Now let's look at the generic case. So wrong answer. Let me see where is the where is wrong. So here LR. So DFS left, DFS right. So yeah. So here we didn't update correctly. So max self D and this longest. So now let's check again. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So here it might be good because the number of nodes is at least 1, so we can actually initialize this D to be 1, but this does not make any difference for this problem. So let's do the submit. Yeah, so this is one valid solution for this problem using recursion and DFS. Let me first simplify the code a little bit, right? So here, yeah, we write these 2 lines. Actually, they are redundant, so we can do like this. Let me do this. We directly call this DFS root left. Then we copy this part, and then we directly call this DFS right. Right. So we can actually delete these 2 lines of code. Now let's do a check. Yeah, it passes all the cases. So it's still actually a little bit redundancy because we used some initialization, but we can do this. Cancel this out, and then write L equals 1 plus this guy, and similarly R equals 1 plus this guy, and then do the update, and then return L and R. Let's do a check. For sure, you can further simplify the code. So with that said, we are finishing the comment on the format or representation of the hyperfunction. So here for the update, we can also do another format, right? So we can use D. We can use D as a variable. So this is D. So let me comment on this part. So we can when we write the function, we can do non-local D, and then we can update here D equals so D, right? Then after we do the DFS, so we're going to return D -1, right? Let's do a check. Yeah, let me fix the one format. Let me delete this one and using the original one. So this is the one, and then let's delete out this line, and then let's take this format because it's more informative. And then we're going to do the self D and self D, right? Let me do a check again. Oh, where's where we're wrong? So self D f root let's see, self root L plus 1 D So here, let me see. D equals max D self D. Let me see. So let me recover the original ones. Let's see. Self D, not root. So this one. L and R self D L. 1 plus this, 1 plus this, then right. So let's see. Let me recover a format. Let's see, make sure it's right. L equals LR equals DFS root left, and RR equals DFS root right. And then let's do L equals 1 plus max LR, and R equals 1 plus max RR, right? And then we do the update. Self D equals max self D, then L plus R minus 1, right? Let's do a check again. Yeah. So we are restart the correct version. So now let's do the submit. Yeah, so that's about it. So with that said, I guess that's about it for this specific problem or this video. So we have a playlist or a channel which actually have more coding problem analysis. So you are welcome to check out. Thank you.